Hey, it's Ross from RossLukeman.com. Today I have the top 9 mistakes I've seen when it comes to batteries and mobile power systems for vans or RVs. These are all over the board and have caused some mysterious shutdowns. As you'll see, some of these are mistakes that I've made or mistakes that I've seen in systems where people called and we had to try to figure out why it was shutting down. So without further ado, let's dive into it. Number 1 is the battery BMS doesn't have enough capacity for that particular system. So I spoke to a guy and his system would work most of the time, but it would mysteriously shut down sometimes when it was charging and sometimes when it was discharging. And what it was is he had 2 100 amp hour batteries, but they could only put out 50 amps each. So they were the Victron Super Pack regular batteries, and they will only take 50 amps in or out of the battery. So 2 of them together was 100 amps in or out of that battery bank. And he had a 90 amp charger. It was a Victron MultiPlus. Out of the box, it's 90 amps, and it was fine by itself, but as soon as the sun came up and the solar would add 10 amps or more alongside the shore power, the MultiPlus would mysteriously shut down. He thought something was wrong with the inverter charger, and it wasn't sure why it was shutting down. On the flip side of that, when he would run most appliances, everything was fine, but when he would run the stove, it pulled more than 100 amps out of that battery bank, and the stove would shut off and a mysterious shutdown again. So what I would recommend is don't just look at the amp hours of the batteries, take your whole battery bank, look at the amps of each BMS. So if it's 50 amps per battery, add that up, 100 amps, multiply 100 amps times your battery voltage. In this guy's case, it was 12 volts. So he could only get 1200 watts. Volts times amps is watts. So 1200 watts was the maximum that he could get in or out of those batteries. And so that's why the electric stove, when it went over 1200 watts, it would shut down the system. And then when the charging went over 1200 watts, that would also shut down. So in the case of the Victron Super Pack specifically, they have a high current model that's going to do 100 amps per battery. Go ahead, I would recommend getting that. I noticed on Amazon just now they have a lot of batteries that are 200 amp hours, but the BMS is only 100 amps. So that 200 amp hour battery is a decent size for a small system. It may work for you, but that 100 amp BMS, just remember, it's only going to put out at 12 volts 1200 watts in or out of that battery. And you may need to turn on the electric stove for 15 minutes. The battery has the capacity to run that stove, but it's not going to let that many amps out of the battery. The BMS is going to limit that, and it's going to shut down on you. So that's just something to look out for. A mysterious shutdown solved in that case. Now, before we get into the other mistakes, if you're interested in your overall power system, not just your batteries, I have a resource that you may be interested in called the Ultimate Van Power Cheat Sheet. It's got a discussion of different battery types actually, and it's going to help you make a decision on which battery type is right for you. It's also got a discussion of the 3 major charging sources for vans and RVs, which are solar, shore, and alternator power. It's going to talk about how each one has a strength, but they each also have weaknesses. And when you bring them together in a holistic strategy, it's going to make sure you have a good charge source no matter where you go out on the road. Whether you're out in the desert boondocking or you're plugged in at a campground, you're going to be covered and you're not going to have to worry about running out of power. And then lastly, there is a really cool diagram that has essentially your whole power system on one page. It's going to show those 3 major charging sources at the top and how that power makes its way through the system, charges your battery bank, and then comes out at your end devices such as your microwave or your phone charger. For instance, how does the alternator power make its way through the system and come out and charge your phone? So it's a really cool diagram that is included with the Ultimate Van Power Cheat Sheet. To get your own copy, all you have to do is click that link below or go to rosslukeman.com/vanpower. All right, with that, let's move on to mistake number 2. This is small cables causing DC ripple. So DC ripple is kind of like a vibration in your system that is caused when you have an inverter. So the inverter is taking DC power from the batteries and it's turning it into AC power, alternating current power. And that causes kind of a ripple in the lines, and that is exacerbated if you have smaller cables. So I got a call from a guy. He had a Winnebago Sprinter van, and he had kind of redone some of the electrical, swapped out the lead acid batteries for some battle-borne lithiums, but they were hung under the vehicle underneath the driver and passenger seat, and the power system was about 12 feet back in the back. And just like the first guy, his system worked well most of the time, but when he would turn on high loads like an electric stove, the DC ripple alarm would go off in his inverter charger. He had a Victron Multiplus. The DC ripple was so high, or the vibration in the system, we could call it, that the alarm went off and the Multiplus inverter charger would shut down. And this was caused by the cables not being thick enough for that 12-foot run. They were 2-aught cables, which is, pretty large. This, can carry 300 amps. And I use this in a lot of systems, but over 12 feet, it was too much. The voltage drop was too high, and DC ripple is reduced when you increase the size of the cable. So that's something to look out for. DC ripple can microcycle your batteries and wear them out faster, and it can also wear out your inverter. You just want to eliminate that from your system. So having cables from your battery bank to the rest of your system that are too skinny can cause DC ripple and shorten the life of your components. So that's mistake number 2, having lines that are too small that cause DC ripple. Mistake number 3, having a battery that's at the end of the line. So with battery banks, we usually have multiples, and it's tempting to bring in positive and negative on one end and just link all the batteries, and in that case you would have a battery that's at the end of the line. So what happens is that battery, because each link is like a little resistor, there's a voltage drop over each link. Once you get to the end of the line, that battery is going to be charged, and it's also going to be discharged less than the battery that's at the front of the line, and to some degree the batteries that are in the middle. So what you want to do is you want to bring positive and negative in from opposite sides. Your positive can come in on this side and link down. Your negative can come in this side and link down as well. And that's going to balance out the voltage drop, and it's going to balance out the charging and discharging amongst all the batteries so that they age consistently together. So that is mistake number 3, having a battery at the end of the line. Mistake number 4 is no fuse near the battery bank. And going back to the guy I mentioned that had the batteries at the front of the vehicle, the power system was at the back. Oftentimes it's hard to know where these fuses go, and you need a main battery fuse, and you want to put it at the source of the power. So not at the power system. You want to go ahead and put it near battery positive when that cable leaves that battery bank on its way to the rest of the system. Put that cable close to the source. And the ABYC standards, the American Boat and Yacht Council, they want you to have it within 7 inches of that last battery positive terminal on its way to the rest of the system. I would say the RV standards are not quite as stringent. If you have it within a foot, I would just say in general, make it close to the batteries and not close to the rest of the system. So that brings me to mistake number 5, which is having the wrong fuse rating or fuse type. So there's kind of a lot to unpack here with mistake number 5. Let's talk about fuse types. There are 3 that are approved for use as main battery fuses by the ABYC, the same entity that I just mentioned. So the first one is an MRBF, marine rated battery fuse. This is referred to as a terminal fuse. And like it sounds, it's going to go right on the terminal. I really like these fuses. They are compact. The one limitation is they're going to max out at 300 amps. So if you have a very big battery bank, and in that case I would put a 400 amp fuse, not going to be able to use the MRBF, but it is definitely usable in the rest of the system. Or if you have, if 300 amps is enough, at 12 volts, that's 3,600 watts. oftentimes that is enough amperage to run your system. So MRBF is approved for use as a main battery fuse. The next one is going to be A&L. These go up to 750 amps. So you can, in my case, I would get a 400 amp and I would put it with a 4-aught cable and have it within 7 inches. Basically, if it's not 7 inches, make that your first stop. So before you have a switch, before you have anything else, your fuse is going to be the first thing you hit when you come out of the battery positive terminal there. So A&L is the second type that you can use. Now, one thing to point out, you can see the A&L 300 amp will go in this small fuse holder, but if you go to 400 amp, they have a larger fuse holder from Blue Sea Systems, and it's made to accommodate those larger cables that you need at the larger amperages. So take note of that. If you're going to go up to 400 amps, do not use this small A&L fuse block. Something to note, Class T is going to be the last type that is approved as a main battery fuse. These are a little bit harder to find, a little bit more expensive, maybe double the price, twice as hard to find, but definitely a tried and true fuse as well. Now, the difference between these is the interrupt rating, and that's why they're approved as a main battery fuse, because the fuses, the batteries can put out quite a lot of current, thousands of amps, right? And we need to be able to stop that power. If there's a short circuit out in the system and the batteries want to dump out all of their power, we need to be able to blow that line and stop that power from getting out of the battery bank. And that's where interrupt current comes in. And so these three fuse types have a higher interrupt current. For instance, the A&L fuse can interrupt up to 6,000 amps coming out of the batteries. The terminal fuse can interrupt up to 10,000 amps. And the Class T can interrupt up to 20,000 amps. So my go-to is going to be a 400 amp A&L fuse. I'll just tell you that. But that's why they are rated as main battery fuses, is that interrupt current ability. So let us move on to mistake number 6, loose connections. So I used to work at a van shop. We got a call from a customer in Atlanta. I'm in Houston, and I had to fly over there. Their system was mysteriously shutting down. It would work sometimes, and then it would just cut out, instantaneously cut off. And what it ended up being, and I figured this out because I poked around under the van. There were batteries, and they were warm. One of the main negative terminal was warm, which is something to look for in these systems. Loose connections are going to be warmer than connections that are tight. So sometimes you can use your hand or use a infrared thermometer. The hot parts of the system, usually there's some kind of problem, or maybe that component is too small for the current going through it, and it needs to be upsized. But in this case, it was a loose bolt on that main negative line coming back to the battery bank. We had some vibration back there, and there was not a locking washer on that bolt. Everything else had a lock washer. That particular bolt did not. It was a human error by the installer, and I would just say have a lock washer or a locking nut. And as I said, I could tell by the heat, and when I looked at the terminals, you could see that some of the plastic had melted, and this is a case where things can melt or catch on fire. So check for the loose connections. Use the locking hardware. Also, if you have torque specifications from the battery manufacturer, go ahead and torque it down to that torque spec. But loose connections in general can shut down your system mysteriously and also cause things to heat up, melt, or catch on fire. So that is number 6. Number 7, increasing the battery bank voltage without looking at other implications. So this came from a guy I spoke with. I do consulting calls, and he had a design for a 48 volt system, and he wanted to fast charge it off of a 48 volt alternator, which was a beautiful setup, but there were other implications which I'll kind of tell you about here. So he had 3 converters to go from 48 volts, his 48 volt batteries, back down to 12 volts to run appliances. So that could be an air conditioner, that could be anything that's 12 volt in your van or RV. So he had 3 converters producing up to 90 amps. They were 30 amps each. And it was $660 for these converters. And I'll just say you may have some efficiency gains with a 48 volt system. You're reducing the amount of current that it takes to do a job. So as you increase the voltage, you drop the current, and that reduces the heat in the lines, and you can use smaller copper lines and things like that. But now you have these converters, so you're adding, in his case, $660. But you also have conversion losses there from 7 to 10%. And you can tell, I got a comment from a guy the other day. He had a 24 volt battery bank, but a 12 volt air conditioner. And he said, man, my converter gets so hot. And when you're off grid, that heat is battery power basically being wasted as that power makes its way from the batteries to the appliance. Any heat is watts. That's watts of power that didn't make it to the appliance. And so I would just say you're introducing costs and you're introducing inefficiencies that weren't there. When you have a 12 volt battery bank with 12 volt appliances, there's no conversion there, and you get almost 100% of the power to that appliance without those conversion losses. So 48 volt is not wrong, but there are implications. The other implication that guy ran into is it was very hard for him to do solar. So he had a small Sprinter van, I believe it was, and so you have limited roof space, and your solar voltage of your solar array needs to be higher than your battery bank voltage. So at 48 volts, you're really looking at 52 to 56 volts actual voltage of that battery bank. And with solar, like with the Victron solar charge controllers, you need to get 5 volts above the battery bank on the roof in order to start the charging process. And so you're looking at 61 volts coming in off the roof to commence the charging of that battery bank. And you could get a bunch of solar panels and string them together in series and get your voltage up high, but you also have to look at early in the morning, say 7 a.m., 8 a.m., the sun comes up, but it's coming in at an angle, and those panels have not quite hit their maximum voltage. Maybe they don't reach a high enough voltage to charge the batteries until 11 a.m. So you've lost the power from 7 a.m. to 11 a.m. when they finally hit high enough voltage to charge those batteries. So in that guy's case, he ended up just omitting the solar, and he was just, in off-grid scenarios, he was just going to rely on that alternator, which is okay. You know, we all pick a strategy. That was his strategy. But there are just some other implications that are not necessarily discussed when you increase the battery voltage and you're able to use super skinny cables. The converters and the solar issues are the two that I would say increasing to 48 volts. It's less of an issue at 24 volts. But that is mistake number 7. Mistake 8, no cold weather provisions. So lithium batteries do not charge below freezing. We can say 32 Fahrenheit would be a cutoff. This particular battery, I think, will charge down to 25 Fahrenheit. But at some cold temperature, you're not able to charge lithium batteries. If they have an internal BMS, they'll just disconnect and the chargers can't get a charge into them. But you need to have some provision. So I'm in Houston, Texas. We have mild winters, and my setup would be to have batteries that have temperature sensors on them and run those temperature sensors to my charger. So if you have a Sterling DC to DC charger for the alternator, it's going to have a temperature sensor. I will go ahead and install that. A lot of these brands, they'll say the temperature sensor is optional. So what we need to do is go ahead and install those so that charger can shut down at a temperature slightly higher than the battery shutdown temperature. So if this shuts down at 25 Fahrenheit, maybe at 30 Fahrenheit, the charger knows to shut down and quit charging the battery. That way you don't have the batteries disconnect and the chargers are going, still going, basically. So if you have mild winters like me, I would just say install all those temperature sensors. If you have a battery monitor like a smart shunt, you can have a temperature sensor that you can get for this, and it will actually wirelessly transmit that temperature. If you use a VE Smart network, you can send that temperature over to the solar charge controller if you get a smart solar charge controller, and basically it'll take the temperature and then tell give that temperature to the solar, and the solar can shut down at those cold temperatures. So it doesn't hurt to have multiple temperature sensors. You know, you want to pay attention to whether it's supposed to go on the negative or the positive. Most of them go on the negative terminal, but you could have a temperature sensor on each battery and connect those up to your chargers so your chargers know what's going on and when to shut down. So that's for mild winters as a minimum. The flip side of that, I've talked to a couple of guys in Chicago that are in the construction trades, and they need to use their vans in heavy winter conditions. They need to be able to charge those batteries even if it's, you know, negative 20 Celsius, 4 below 0 Fahrenheit. They need to be able to use those systems, and in those cases I would get the batteries that have the internal heaters. They've got Battleborn has one. You hit a switch and it's going to use its own battery power to heat itself, so it's chargeable. They also have some that are starting to come out from other brands. There's one on Amazon, LI Time. Sometimes you're going to have to pay a little bit more to get the fancy model, so to speak, but they have one that if it's too cold to charge, it'll actually take a charge from solar or alternator, but it's going to run its internal heater, and that power is not going to get to the battery cells. It'll disconnect the battery cells. It's going to heat them up, and then when it gets to a set point temperature, it's going to reconnect internally, and that charger is going to quit powering the heater, and it's going to charge the actual battery cells. So that's kind of an automated way. So depending on how heavy your winters are, either do the temperature sensors if you have a mild winter, or frankly, everyone should have the temperature sensors, but I would get the internally heated batteries if you're going to be using your system through a heavy winter as well. So hopefully that was helpful for you. Mistake number 9 is no external battery monitor. So that's why I brought out the smart shunt here. It could be a Seamarine Pico, could be a Victron smart shunt. But basically, a lot of the batteries nowadays, they're going to have a Bluetooth app, and you're going to be able to see the state of charge of each battery. But these battery banks, they have multiple batteries, 3, 4, 5 batteries sometimes. And so you're going to pull up 5 different batteries on the app, and you really need the external battery monitor that's going to act like a fuel gauge for the aggregate battery bank. And it's going to tell you the state of charge for all 5 batteries or whatever. And then also this is networkable to things like a Serbo GX that it'll bring in the battery data, but it's also going to show water tanks and temperatures and propane tanks and things like that. So battery monitor is going to be your minimum when it comes to system monitoring. You want to have this fuel gauge, essentially is what it is. You want to have this as a minimum. And then also with things like the Victron Smart Lithium, they have a lot of data that's reported from each battery, but they don't have a state of charge because they don't know how many batteries you're going to string together. So in that case, you would get one of these. And this is a 500 amp model that is pretty much as large as I use, but they have the 1000 amp and the 2000 amp models. So you can string together 20 batteries and then have that single battery monitor as the last gateway into the battery bank. Is going to take an accounting of everything coming and going out of that battery bank. So have an external battery monitor would be my takeaway from point number 9. So those are my 9 mistakes from batteries. As you can tell, these are a lot of shutdowns that I've run into, and a lot of issues I've run into from real vans and issues that we've had to figure out that weren't always obvious. So hopefully that was helpful and maybe saves you some frustration. But again, if you want more help with your overall power system, be sure to grab a copy of the Ultimate Van Power Cheat Sheet. Just click that link below or go to rosslukman.com/vanpower. So thanks for watching, and I'll see you in the next video.